Yes, good evening to all the participants. So, welcome to day 7 session on molecular phylogeny. So, today we'll be discussing on phylogenetics basics and character-based methods. We also discuss on one tool for working on phylogenetic trees. So, that is phylip. We discuss even how to use phylip on today. So, this is what today's session. Before going to today's session topics, can we recap the last session topics? Yes, very good. So immediately I got answer from a participant, Gauri. Yesterday's topics are TDPJ cluster. Okay, we have seen cluster in various public domain databases. We have discussed in DNA Data Bank of Japan. We have discussed in genome.jp. We also seen the cluster W is available in EBI. So I have majorly provided demo on EBI cluster W as well as genome.jb cluster W. And then we have gone to blast. So we worked on, even the others can interact, very good. So we have worked on blast. So I have taken you to the NCBA blast, but I told you we also have a blast in Uniprot, and we also have in almost all the public domain databases. In EBA we have blast, and we have in DDPG also we have blast. But I provided demo on NCBA blast on yesterday. So other than a blast, we have also gone through PHA blast and PSA blast, isn't it? Then we have discussed on amino acid substitution scoring matrices like PAM and BLOSSOM. And we also discussed on the steps in FASTA algorithm, including BLAST. Okay, so this is what we majorly discussed on yesterday. So now let me ask you some questions. Okay, like expand PHI BLAST and PSA BLAST. Expand PHI BLAST and PHI BLAST. So this is my first question. The participants try to answer. What is PHI blast? So first you can tell about that, then we can go with PSI. Very good. PSI blast stands for position specific iterated. Can any participant can give the expansion of blast? What is the expansion of blast? And what is the expansion of FASTA? There are these are pairwise sequence alignment tools. Okay, these are of course most important tools in bioinformatics. Very good. For BHA, it is pattern hit initiated. And how about the expansion of blast and FASTA? So there is an expansion even for blast and FASTA. So FASTA, I'm mentioning about the tool. So both are pairwise sequence alignment tools. Basic local alignment search tool. Very good. That's the answer for blast. How about FASTA? Any expansion is there for FASTA? So default you can able to understand we use a local alignment in blast. No doubt in that. But in FASTA we use even global alignment. Okay, so that's also a difference between the blast and FASTA. Just because FASTA is going to use a global alignment, so it is faster when compared to the blast tool. So this is how we can also find a difference between blast and FASTA. What is the expansion? Don't you know the fast alignment? So that's the expansion of FASTA. Okay. Now I come up with one more question. If you are comparing human and E. coli, if we compare human and E. coli, which amino acid substitution scoring matrix is best? So I just provide you for more. I mean, the question is not complete at present. So now I'm going to give value. So the value is PAM 1, PAM 250, Blossom 10, Blossom 100. Okay. So actually, PAM1, the range is from 1 to 250, and Blossom is from 10 to 100. Okay, so which is best? I mean, if you compare human and E. coli, so is the Blossom is best? If Blossom is best, tell me the value. Which is best, Blossom 10 or Blossom 100? So good. The Blossom is the answer, but even in Blossom, I have given two values, Blossom 10 and Blossom 100. If we compare human and E. coli, which value we choose? These are the National Common Entrance Examination questions, like in a GATE. Heard about GATE to entry into IITs and NITs? They ask these kind of a questions. What is the best? Even they ask like Blossom 30, Blossom 45. I didn't ask 30, 45, something like that. I'm just asking you Blossom 10 and Blossom 100. Good try Blossom 62, but I asked only Blossom 10 and Blossom 100. It's not in that choice, whatever they provided. Blossom 10 is perfect. Blossom 10 is perfect. Okay, so that is we compare 10% similarity and more than 10% similarity. So this is the lowest similarity. Okay, Blossom 10. You know, whatever we consider the PAM 250, the PAM is just quite opposite to the of Blossom. The equivalent of PAM 250 we have discussed, isn't it, on yesterday? It comes around Blossom 45. If it comes around Blossom 45, okay, Blossom 10 is still lesser. Blossom 45 we mentioned, if we have 45% similarities in comparison of query and database, we use Blossom 45. At least we should have 45% similarities. But Blossom 10 mentions we should have 10% similarities and above. So obviously, no doubt, Blossom 10 is the amino acid substitution scoring matrix we use for comparing human and E. coli sequences. Participants join on time, so you don't even accept the Google invite and you're joining very late. Join before 7 p.m. if you don't accept the invite. Okay, now let me come across. Moreover, we are recapping, and this is most important. Okay, so whatever you study, I'm just recapping the last session, isn't it? If you come late, you don't know what exactly is happening here. Okay, then I think just because few participants joined late, I can ask you a few more questions. Just I completed the difference between PSA and PHI and the difference between PAM and Blossom. The next, what is the tool we can use? Okay, if you compare mRNA query versus sequence in database, protein database sequence. See, we have, if you pasted mRNA query, and but after pasting mRNA query, if you want to get a protein sequence, what blast tool we use? There are five versions of blast. You remember? Can you type the five versions of blast, whatever you know? Yesterday I provided demo on the versions of blast, isn't it? Not everything. Blast number six. No, actually blast 10. Blast 10 for nucleotide query versus nucleotide database. Okay, blast 10 is nucleotide query versus nucleotide database. Then what else? You know, blast 10. Very good. We got the answers. Blast 10, blast B, blast X, T blast X, and T blast X and T blast N. T blast N. Instead of T blast, we have T blast N. This alone is we have to correct as T blast N. Good. So my question is, what is the like if you use an mRNA query? Can we see the answer now? So I'm going to take you to the answer. So just 1 minute. So for not forgetting, I'm showing you the picture of the blast tool. So we have seen plenty of formats. One is table format, another is this kind of a text format, and another is a graphical format. So first I show you this text format. So what is mRNA versus protein? Now tell me. Now just type the answer. If you're using an mRNA query versus protein sequence database, what tool we can use? Okay, sorry. I mentioned as T-Blast, isn't it? 1 minute, 1 minute. It's excellent, right? See, actually, there is some wrong. Very good try, even from a participant. You have corrected me. Actually, we have T-Blast X and T-Blast M. Whatever I showed, like a T-Blast is not T-Blast. This is T-Blast N. This is T-Blast M. Also, I just write here, which is T-Blast N, This is T-Blast M. So this is missing here. But if you see here, we can see this T blaster. Okay, you can see the T blaster. Also, we have T blastex blasters. Okay, what is the answer for mRNA query versus protein database? Whether you type the answer, can I check? T blast. T blast. Yes, good. The answer is blastex. The exact answer is blastex. Very good try. And definitely you can anticipate this because uh, this is what a examiner can confuse you. What query versus what database, and even they can ask you some kind of a problem. This is how we can expect in national competitive examinations. Very good try, participants. There is nothing actually. Even if you make a mistake, okay, you are correcting it, isn't it? But others even not correct it. But even though you typographical error, I understand. So there is no need to ask sorry. But very good try from the participants. Okay, so that's what I can mention. So I appreciate your kind of an involvement in interaction. Now let me take you to the molecular phylogeny. So actually, in phylogeny, we discuss on the phylogenetic basics, molecular clock theory, and tools for the character-based methods. There are actually two methods in phylogenetic tree construction. One is character based and the other is distance based. So, more about the character based and distance based, these are the two methods I told you for phylogenetic tree construction. We'll be discussing in the subsequent slides. Oh, again, we are getting this. Okay, now let me take you to this introduction to phylogenetics. What is phylogenetics? So, phylogenetic trees illustrate the evolutionary relationships among group of organisms or among a family of related nucleic acid or protein sequences. So, you can see this tree. This is what we call it as phylogenetic tree, and the output we call it as phylogram. The whatever we analyze in the phylogenetic tree, okay, we call that as grams. We call it like a phylogenetic tree is what we call it as a phylogram. And what are the other outputs? We can also, if you the same output, if you get like this, okay, like how if you get like this, okay, so this is actually an inclined straight line. It's an inclined straight line, isn't it? But this is something like a curve. Okay, it looks like a curve. So the phylogram, now we call it as curvogram. And yeah, how to infer this tree? If we have a tree, if 1 minute, I can close the WhatsApp and come. Yeah, now let me take you to the PPT. I close the previous. Yeah, so I was explaining you. So this is a phylogram, example of a phylogram. But instead of having a inclined straight lines, if you have a curves, we call it as a curvogram. Similar kind of relation you can able to see there. And what are the other trees we have? So that we can see first how to infer the tree. Then we can see the types of trees, types of tree outputs. Now, first, if you see this, According to this tree, we can able to infer snakes and birds, okay, reptiles and aries. These are more closely related. So this is first inference. Second inference, so next to the snakes and birds, these are closely related to turtles when compared to mammals. Okay, snakes and birds are closely related, no doubt in that. And snakes and birds are closely related to turtles. And if you see which is more closely related, whether birds or snakes to the turtles, if you compare it, you see the length of these snakes, okay, the length of this tree is small, but the length of the birds is large. So we can able to tell that if you see this entire length, so see that from turtles, you have to take from the turtles and then you have to come here and if you have to see this. So this is a shorter path when compared to this. If you take to the birds, you have to take up to this. You have a lengthier line. So it is we can able to infer the snakes are more closely related to turtles when compared to birds. So based on the length of the tree. So here the trees are generated, the trees are constructed based on distance. How much genetic distance, the evolutionary relationships are measured through evolutionary distance, that is genetic distance. We remember in genetic distance we have discussed like Lavenstein distance, Hamming distance. So what is the distance generally? How many number of mismatches and gaps present in if you compare two sequences, isn't it? If you compare a turtle sequence and a snake sequence, this is not an entire protein. You can able to construct a phylogenetic tree with one protein, only one protein at a time. So this can be a hemoglobin, or it can be insulin, whatever it is, okay? Only one protein you can compare. For one protein of all these four species, if you compare how to link, so whether the insulin hormone is generated, the insulin hormone from snakes is generated from turtles. So this is something we can able to check, okay, a relationship if we construct such a kind of it. Okay, and again I'm telling you here this tree is constructed based on distance. The distance is number of mismatches and gaps, so only you can see the difference in distances. Okay, and if we can able to create a tree based on distances, so this phylogram we can call it as phenogram. So phenogram, we are constructing the trees, okay, based on characters as well as distance. What do you mean by characters? So characters or matches, number of matches between turtles and snakes. If you have 110 amino acid in turtle and 105 amino acid in snakes, how many amino acids are matching with each other? So that we consider as characters. Distance, how many mismatches and gaps together. Okay, that's what we discussed earlier, isn't it? So if you we consider both the characters and distance, the phylogram we call it as phenogram. The phylogram can also be classified as cladogram. This is the second type. Either it can classify it as phenogram or it can classify as cladogram. According to cladogram, we can able to construct the trees only based on characters. We don't find any distance. So in this case, if you create a kind of a tree, okay, we can have a kind of equal lengths. We can have a tree in the form of equal lengths. Okay, so this is how we can able to find a cladogram. In cladogram, you don't have different kind of lengths. So if you see this length is same and this length is same, something like that. You don't find a difference in lengths. Okay, but you can able to see see the relationships of it. If you have A, B, C, so B is linked with C, B is also related with A. A to C, if you have some kind of a distant relationship. Something like that we can infer in cladogram. But how much distance? This can measure only through phenogram. Okay, and related to on another output of phylogenetic trees. So phylogenetic trees, if you have such a kind of, I told you, we have, if you have a kind of a curves, we can have curvogram. We can also have soupogram. So you have a different kind of output in soupogram, a style of how we show the trees. So the based on style, we can also find these kind of outputs, curvogram and soupogram. You know, so whatever we are constructing this, we call this as phylogenetic tree. But there is also something called evolutionary tree. What do you mean by evolutionary tree? What is the difference between phylogenetic tree and evolutionary tree? You know, in phylogenetic tree, so we consider characters and distance for construction. But in evolutionary, other than characters, distance, in evolutionary, we also consider time. So we have characters, we have distance, also time. For example, if you whether we have a such a kind, no example. Now I can draw and show you an example. So if you have a kind of a tree like this, okay, and like this, okay, think like we have a rooted tree, okay, and if we have this is C for chimpanzee, H for human, and this might be a gorilla, and this might be orangutan. Okay, so what is the evolutionary relationship between? So if you see the evolutionary tree, so obviously can see the tree lengths are different here. Each and every length is different here. So of course this is a kind of a phenogram in the phylogram category. Other than that, if you see the Homo sapiens emerged from chimpanzee over 10,000 million years ago. 10,000 million years ago. And chimpanzee might have originated from gorillas again from 10,000 million years ago. So we have such a kind of time scale. We have a time scale for each and every ancestral species origin. Okay, so instead of mentioning the characters and distance, also if you mention the time scale, they mention something like a time scale. Okay, and if they mention a time scale, then obviously we have to get like this. So according to this, human is linked with the chimpanzee, and next to the chimpanzee and human, it is linked with the gorilla because of shorter, shorter thing. So might be the orangutan, we can take some more a lengthier thing. So if you have a kind of a lengthier thing, then obviously orangutan is distantly related. So we can stretch a line like this. Okay, this is more distantly related. So this is how the span. Okay, we can also construct the tree based on the span of these species. And if you want to construct such a kind of evolutionary trees, okay, we can use different websites. The most used websites are Phyling, Phylogenetic Inference Package. This is the name of the tool. Here we have 35 programs. We have 35 programs to construct the phylogenetic trees. Okay, and we also have few more tools like PAUP. The PAUP stands for phylogenetic analysis using parsimony, and we also have PAML, phylogenetic analysis using maximum likelihood. So we'll be discussing more about this if we see in the subsequent slides. Now about rooted tree and unrooted tree. So these are the types of trees. If you see the tree, okay, so this is what rooted tree. Why we call this as rooted tree? We have a common root. From this common root, so you can find A and B are closely linked with each other, and C and D is linked closely with each other, and C and D and A and B are linked with each other when compared to E. So this we can able to find it in rooted tree. But whereas in unrooted tree, we don't have common root like this. Only this common root, you can find AB is branched and CD is branched and also E is branched. but we don't have any curve. Where can we draw the common root? Whether we can draw here, it's not possible at all. So we call this as unrooted tree. This is how we majorly classify rooted tree and unrooted tree. Now we discuss all the parts of tree. So whatever we find, this A, this point, this we call it as internal node. Okay, this we call it as internal node. So this also an internal node. So there are totally 5 internal nodes. Then how about external node? Do you find the external nodes? So what is this? This is what external node. And of course, if this is a common branch, this is also an external node. So these are the external nodes, and of course the uh, right. Actually, sorry, I just made a just quite opposite kind of a inference, isn't it? So this is actually external nodes, and this is internal nodes, isn't it? So external is present outside, internal is present inside. So two internal, 5 external. In rooted trees, in unrooted trees, we have this as internal node, no doubt, and obviously again if you see external nodes, we have 5 nodes. One, two, three, four, five. So these are the parts of the rooted tree as well as unrooted tree. Okay. Now let me take you to the next concept, molecular clock theory. So we have three molecular clock theory. This is actually molecular clock theory. One, this was proposed by Zuckerland and Pauling in early 1960s. According to them, for any given protein, except mutations in the amino acid sequence for the protein occur at constant rate. For example, the time of evolution from chimpanzee to human, I mentioned you 10,000 million years. Then obviously, the immediate ancestral species of chimpanzee is gorilla. So from gorilla to chimpanzee, once again we take the constant 10,000 million years. That's what the Chunkerlet and Pauling states. So again I'm telling you, the accepted mutations in amino acid sequence of the protein occur at constant rate. It means the time of evolution. Accepted equals mutations that allow protein to function without it. Okay, so this is something about this is a basic theory actually. Okay, proposed by Chunkerlet and Pauling. Now about the molecular clock theory too. This is a modified one when compared to the previous one. Rate of accepted mutations may be different for different proteins. See, if you see the insulin protein, we have seen an example, insulin ligand protein, when we compare the Homo sapiens, okay, with other species in Plaster as well as Fasta, we got the most closely related species is Sususcrofa. Okay, this is what pig Homo sapiens are more closely related with this. So only they are sacrificing the Sususcrofa for insulin in 50 years before. And also we find in Fasta tour as post Taurus. Okay, even this is also closely related with Homo sapiens. So what you can able to understand whether we have originated immediately from the ox, is it so? Bovine? No, this is not an ancestral species. We are, even pig is not the ancestral species for human. So obviously one can able to understand that whatever evolution has start as completed up to pig or bovine. Okay, so from here there is no such evolution. I mean, mutations are happen. I mean, the mutations have happened in the subsequent thing, but here you don't have any mutations. So only the Sususcrofa and Homo sapiens are closely related. If mutations happened in the chimpanzee and gorilla, just because the mutations happened, you can find a variation with respect to the characters. But here, these species, so what you understand in insulin, it is not correct. Okay, so this molecular clock theory holds best for insulin example. But if you take hemoglobin, hemoglobin, once again, if you see the chimpanzee has more closely related with the human, and even myoglobin, muscle protein, this is also closely related with the human. Okay, so many of the proteins linked with the ancestral species, but not all the proteins. That's what molecular clock theory 2 signifies. And now molecular clock theory 3. So according to this is again a modified version of clock theory 2. If A and B differ by K accepted mutations, then roughly K by 2 mutations have occurred since divergence. Then K by 2 mutations are proportional to the times since divergence. So one can understand. So instead of K accepted mutations, here we understand we have a K by 2 mutations are followed. Okay, this is what molecular clock theory 3. So if you see, this is an example of phylogenetic tree of fungi containing, there are different fungal species available, isn't it? If you want to check the similarities of the fungus, okay, the family of fungus groups, we can able to see this tree. So the tree can also be like this, like a rooted or unrooted, and the tree can also be in this circular plot. Okay, we can also have in this shape. So there is a tool called ITOR. This can create such a kind of a, if you have a more number of sequences, see more than 100 sequences are there. If you have more than 100 sequences, you can't able to check the relationship using these trees. Instead, use this kind of a relationship. Okay, the trace can also be in this form if you have more number of sequences. Now, let me come to this phylogenetic flow chart. In, what are the types of the methods of phylogenetic tree construction, and which method we have to use for our experiments, for our project? That we'll be discussing now. If you see the phylogenetic flow chart, okay, so generally, before going to this flow chart, I just explained you the methods, then I can link with the flow chart. If you see the methods, there are two methods of phylogenetic tree construction. Number one is character based. Number two is distance based. Okay, this is extracted from the universal textbook Bioinformatics by Mount. Okay, character based and distance based. These are the methods of phylogenetic tree construction. And this can also be classified in two dimensions, like based on clustering and based on the objective function. The clustering, if you have closely related groups, we can cluster. If you're using a function to link the species, then we call it as objective function, kind of a classification. Okay, so if you see the on clustering, we don't have any character based method, but based on the function, a probability distribution function, we have two types of methods in character based. One is maximum parsimony, the other is maximum likelihood. So these are the two methods of character based for phylogenetic tree construction. And now, if you see the distance space can be further classified, yeah, based on clustering and objective function. Based on clustering, we can use UPGMA method, unweighted pair group method of arithmetic mean. Okay, so this is actually a problem based. This is also an algorithm. This is an algorithm used to create the phylogenetic trace. So to work on this algorithm, we'll be discussing it on tomorrow. Today we'll be discussing the basic information. And this is also another algorithm called neighbor joining. Okay, this is also a bioinformatics algorithm for construction of algebraic trees. So both uses the clustering based, distance based approach for phylogenetic tree construction. And if you see the based on function, okay, we have two more methods under distance based: minimum evaluation and least squares. Minimum evaluation and least squares comes under distance based, but it comes under objective function. Now let us see how to use the method. Okay, if you have a family of sequences, if you have more than two sequences, then only I told you we can go with multiple sequence alignment, isn't it? So initially, if you see the output of pairwise sequence alignment, we take it as an input for MSA. And output of MSA, we take it as an input for phylogenetic tree construction. This is how we generally use it. So this, whatever we studied in the earlier sessions, have a continuous kind of sequence in usage. Okay, so if you see MSA, so what is MSA? Again, a series of pairwise sequence arrangements, isn't it? So what for MSA is just, of course, to link the species. If you want to link the species to check the evolution, conservancy of the species, then we can also infer through phylogeny, isn't it? So the output we take it here. So generally we take a family of sequences, that is a multiple sequence alignment input, whatever we give, and we can give an alignment. Or else you can also, whatever I'm telling is an alignment, this is an output of MSA. This is an input of MSA and this is an output of MSA. And whatever output of MSA, we can use it for phylogenetic tree construction. So after this, whatever you do, this or tree construction. Okay. And if you see here, uh, if you have strong similarity, that is, if you compare human, chimpanzee, gorilla, orangutan, which is more closely related with hemoglobin, then we have to use either, this is not followed, don't follow this, this is wrong. So we have to follow either maximum parsimony or maximum likelihood. Either maximum parsimony or maximum likelihood has to be followed if you find more similarity in characters. Okay, for example, even the chimpanzee and human, I believe, more closely related. I mean, 100% similarity. So something like this, if you have, go with this. But what to choose, even MP or ML, will be finding these answers in the subsequent slides. Now let me see if they have a recognizable similarity. That is, we don't have a strong similarity, but somewhat okay, 90% similarity or 50 to 90% similarity. Then better go with the distance based. Okay, for this only we can go with the distance based. Distance based, you can use any of these methods. If you want clustering, use these two methods. You use any of these two methods, and if you want a function based, use any of these two methods. Now, in this slide, we discuss on the formula to calculate number of trees. Actually, to calculate the number of rooted trees, this is the formula: 2n minus 3 factorial divided by 2n minus 2 into n minus 2 factorial. For example, if we have 5 number of total sequences, then how we'll be getting it for rooted trees? Okay, if you have 5 sequences, so if you use this in the formula, 2 into 5, 10 minus 3, obviously 7 factorial, divided by 2 power n minus 2 is 3, isn't it? And then now 5 minus 2 is 3 factorial. How to write the 7 factorial? So if you want to 7 into 6 into 5, okay, 7 into 6 into 5 into 4 into 3 factorial. This is how we can write. Divided by 2 power 3 into 3 factorial. So 3 factorial we can cancel. What is 3 factorial? 3 into 2 into 1. So instead of 3 into 2 into 1, I use like 3 factorial at the top. So now we have cancelled it. 2 power 3. How much is it? So I can, I might have written as 8. Okay, I have to go to the next slide. I can take an eraser now. Eraser, instead of 2 power 3, I can write 8. Okay, so if it is 8, so 4, 2, 3. So if you multiply, obviously get like 1.5. And unrooted trees. For this, you can use this formula. Similarly, you can use the number of 5 here and you just calculate it, we get 50. So for rooted trees, we get more. Okay, we can get a possible number of rooted trees is not 5 if you have 5 number of sequences. Do you understand what I mean by that? If you have, for example, so whatever we can see here, this is actually one tree. I told you, if you have 5 sequences, we can able to create around 105. Here you can create 15. If this is one of the one out of 105 tree, how about the two? The two can be also like this: B A C D E. You got it? How I am telling. So this is actually one of the, or you have to link here, isn't it? Not this. So I use an eraser. Sorry. Yes. I just taken to this slide actually. Yeah. So just take an eraser. You don't have a relation like this, but you have a relation like this. Okay. So then obviously can understand even the instead of A B we have a B. This also a type of a tree. Still it's a type of a tree. So this is 2 out of 105. Like this, we can have a different kind of trees. Okay, possible number of trees are around 105. Similarly, even for this. So B comes there, A comes here. Still it's a different. Okay, like this we have 13 more combinations. So this is something about how to calculate rooted and unrooted. If you see number of taxa refers to the number of sequences. Okay, and number of unrooted and rooted. If only if you have minimum 3 taxa, then only we can calculate the tree. If you have just 2 OTU or 2 taxa, if you join this is not a tree, but this is a line. It's just a line. If only if you have this one more thing, then only we can have a kind of a tree relationship. Okay, so if you want to construct a tree, minimum you have 3. For unrooted tree, we have one can be created with 3 taxa. But rooted trees still we can create 3 trees. Okay, we can create 3 trees. This is an unrooted tree. For a rooted tree, we can have a different thing. Okay, like this, like this. Okay, however it is. Okay, we can have a different kind of a combinations. Similarly, similarly, uh, even still this is not right. Actually. That should be equal distance. So okay, something like this, A B C. If I have a tree like this, then B A C. Like this, we can have a possible 3 types of rooted trees. Similarly, for 4, 5, 6, 7, 10, how many trees we can able to create? Okay. Now let me go with this distance based and character based whatever we discussed. So which is left out, weighted neighbor joining and Fitch Morgalish is also a distance based method. But in character based method, we have maximum parsimony and maximum likelihood. So character based methods, maximum parsimony, maximum likelihood. What is maximum parsimony? In this technique of maximum parsimony, we generally compare the characters, okay, during the phylogenetic analysis. And if we see, this is a tree that shows the evolution of relationships based on common ancestor. Okay, and if we see this maximum parsimony, so we can see it here. When drawing a maximum parsimony tree, the tree is always the shortest possible tree with minimum number of taxa. Okay, so the reliability of maximum parsimony is very high when compared to likelihood. The name itself is likelihood. Parsimony is most similar characters in the sequences can be compared. Okay, but next to that, we can go with the maximum likelihood. If you have 100% similarity, 99% similarity, go with parsimony when compared to likelihood. If you are comparing with human and gorilla, we may have some kind of a distinct characters. So go with likelihood, even for that case. So this is how we can distinguish the parsimony and likelihood. Okay, and now let me take you to the parsimony. So here we see one more example. We have 5 sequences. Okay, A, B, C, D, E. This is a nucleotide sequence. And if you see the first character, this first character, okay, from all these 5 sequences, this can be Homo sapiens, chimpanzee, gorilla, orangutan, baboon. So if you compare like this, the human and chimpanzee, okay, so that is GG, and here you have GAA. So here, why we are giving this GA, So instead of A, if it has a tendency to get mutated to G, if it has a tendency to get mutated as G, okay, then how, whether we get a kind of a close related tree or not, that we can able to check with the maximum parsimony. And here, if you take this is the side 2. Side 2 means the second character. D, D, C, C, C. Okay. So if one is mutated, okay, like C to D. So here you can see the T is mutated to C here. Here the G is mutated to A here. But still you see, even though if you see this uh, ancestral species from human to, I mean, gorilla to chimpanzee, chimpanzee to human, okay, still there is no such difference between human and chimpanzee here. But you have a G here, that is for gorilla. But the gorilla has to be linked here only, isn't it? Either human or chimpanzee. Why we have to link here, Because from here onwards, you find a transition. That is, orangutan and baboon is of course close related according to this first site. But this immediate ancestral species of orangutan, okay, is having a kind of a mutation. Okay, instead of linking a, a kind of a tree here, we are linking a tree with this next species, that is with the ancestral species. So only we draw a line here. You got it? Because we find a transition immediately after the from the ancestral species. Similarly here also. Here also, if you see for the side 2, okay, so there is a mutation happened actually. There is a mutation happened, so it can also be linked here. Okay, this is how we can understand in maximum parsimony. So we compare only characters. We don't use any distances in parsimony as well as likelihood. But how to draw this line? This is based on the transition. Okay, the transition of mutations happening from one ancestor to the next. Next, we come to the maximum likelihood. Maximum likelihood is one of the most used statistical methods that analyzes phylogenetic relationship. I told you, if you are comparing a more close related species, use parsimony. Next to that, you can use likelihood, like 99, 98, 99, 100% similarity, use parsimony. If it is 92, 97, something like that, go with the likelihood. This is how we can see. Okay. And this is how we can understand. And this method will analyze phylogeny based on the probability model. Okay. That's the difference between parsimony and likelihood. And this take both mean and variance in consideration. Okay. And maximum likelihood is obtained on the given genetic data of a particular organism. So there are both advantages and disadvantages of using this statistical method, whereas that is purely a character-based method in parsing. So this is a difference I can able to find parsimony versus likelihood. So we can find a tree like this when constructing using the likelihood. And the major differences is a technique of drawing the tree with a minimal number of characteristic changes. But here is a technique of drawing tree with the maximum likelihood between genetic data. Okay, so we are not just using the characters alone here in likelihood. That's what they mentioned. Still, it's a character based because we are not fixing a distance. We randomly we can use the we use a probability kind of a thing, and we use mean and variance for construction of trees. That's what they mean. And here the characters consider a low in number, but here it is high in number. Branches are long, short trees. Less reliability, but this is more reliable. Okay, because it's using a quality functions. Okay, now let me take you to the tool. So what is the tool and how to use the tools? Now we discuss it. So I told you we can use phylogenetic trees, isn't it? So, I mean filing for drawing for phylogenetic trees we can use phylogeny inference package. So we have to go to this URL. I think I pasted this URL in WhatsApp group. So in Google, if you default type the file, it will take you to this. We can able to download this program. Okay, and even we have instructions and we have even sources. Okay, I've already downloaded a earlier version of Phylib. So I downloaded as Phylib 3.69. If you see here, okay, we have okay, let's view. So we have three folders: document, exe, and src. I told you in Phylip we have totally 35 programs. So if you click exe, you can see these 35 programs. So we can see 35 programs. Okay. And in this program, so what are these programs meant for? Drawgram. There is a program called Drawgram. This is used for construction of rooted trees. Drawgram for rooted trees. Draw tree for unrooted trees. So the symbol also shows here rooted tree, unrooted tree. Okay. So similarly, if we want to construct trees based on character-based methods, so character-based method is maximum likelihood, isn't it? So if you are using a DNA sequences and if you want to construct using the maximum likelihood, use DNA-ML. DNA-ML is used to construct the phylogenetic tree for DNA sequences using likelihood. And similarly, DNA pass for parsing. And for protein, we have PROTPOS for and ProML. PROTPAS for parsimony, ProML for maximum likelihood. Okay. We also have a few more tools like that. So again, I'm telling you, for drawing rooted trees, drawgram. Draw tree for unrooted trees. So maximum likelihood for DNA, DNA-ML. For protein, ProML. Okay, and for calculating the distance of the sequences, distance of the protein, say, for that we use protist. And if you have want to calculate the distance for the DNA sequence, DNA dist. Like this, we have different programs actually. For using these programs, I can set the trees. You know, whatever I downloaded, Phylip 3.69 is an offline tool. So how to work on this tool? So to work on this tool, if you don't know anything about how to work on it, better use the documentation. In the documentation, they have mentioned very clearly how to use the tools. For example, if I want to use uh, distance based or character based, okay. So for example, now I'm going to use first draw tree for rooted tree diagram. So draw no, unrooted tree to the draw tree. Rooted tree to drawgram. So I'm just opening, double clicking this drawgram. If I open the drawgram, okay, so this is the source. If I double click the source, you get this kind of uh, HTML page where you can able to see here how to copy and paste. So what exactly I have to copy? So we have to copy the multiple sequences as an input, and if you give an input, you can get an output. So we should have multiple sequences. So for downloading the multiple sequences, can we try with the Uniprot? So Uniprot is easier, isn't it, for downloading the multiple sequences? So I take you to the Uniprot KB, type the incident, let us see whether it works or not. Human incident ligand, bovine, dog, Gina plate, Suscrofa. I use this five spaces totally download, and I'm going to use FASTA canonical compression no, click download. So this is incident file sequence that we have already seen. even in Bioinformatics. So this is actually insulin 5 sequence FASTA. Okay, 5 sequence FASTA. We already saved it. Okay, still I'm saving it fast. Dot FASTA. Okay, so whatever I saved it. So can we give us an input? So whatever a FASTA we have, okay, that dot FASTA, that I copy it. I have this file hyphen 3.69 in F drive. Inside the F drive, inside the exe, we have to paste it. Now I pasted that FASTA format here inside this. So let me check how to work with. So now I'm using a DOS prompt. For DOS prompt, type command here. So we get a DOS prompt here. To increase the font size, go to the settings. Uh, Appearance is okay. No matter, increase the size of the font. Interaction, white space, appearance. Or just I can see there is a possible pause. Settings. Okay. Control plus S increasing. What is the necessity to go to settings? I'm using Control plus to increase the font. So now I have to go with the F drive. I've gone to the F drive. So I have to go to the file. So I'm typing change directory and to go to the exe folder. So typing this. Now I want to work with a program called uh, drawgram. So type drawgram. If you type drawgram, so because that is a exe file, it takes you inside. Now you find a blue color kind of a screen. Now please enter a new file name. What is that? Insulin. So I might have typed a smaller file name. Insulin underscore 5 seek underscore fast underscore 5 seek underscore fast. Is that? Yes. Capital I, capital F. Capital I, capital F. So, and this is fast. Unexpected enter file. Actually, this FASTA file is not taking. FASTA format is not taking. I believe we have to give only the sequence input. Okay, so how exactly they are provided. If you study the text, you can able to understand how to use this. Routed tree, routed program. So as with dot tree, a font file, a tree file, the tree file in tree. So better, I think I can go with another thing. So that is, I illustrate presently prod test and UPGMA, how to draw a tree using UPGMA. And tomorrow I can explain you this. Okay. So first about the prod test. So if you want to know about the protest, okay, so I believe you, in the program you have to take only the sequence. You should not take the faster format. If you take the sequence alone, it work. I can try and then I can show you to you. But before that, I can show you how to calculate the distance, and then after calculating distance, how to construct a tree using UPGM. So for calculating that routine distance, prod dist is there. So how to calculate the distance? If you click this source, okay, you can come to know. Simply they're asking you to use the sequences. So they're asking to use the sequence in this format. So how to use this format? Now I'm going to explain you. So I'm going to take you this. Okay, just I need 3 to 4 minutes to complete. I have to open answer. So opening something else. I have to open initially notepad. I just open the notepad, and after opening the notepad, I just go. I have this. So instead of having like this, okay. So according to the format, you know, so according to this format, so what they're mentioning, the first five mentioning how many number of sequences, and this is the maximum length. Okay, for example, here I have to give five sequences, so five, press tab space, and then maximum you can provide like what the maximum whatever you provide should be the maximum. So I can give something like 130, more than 110. Now, how we have to give any keyword followed by the sequence. Now I'm going to give something like human. Now press a tab space. Okay, press a tab space. Okay, any wrapping is there? If wrapping is there, remove the wrap. Now I remove the wrapping. Press enter. Now we have to use the second thing is suscrofa. I can better use like pick. Okay. Now this line is not needed. One day I need the sequence alone. I take the sequence alone for the pick. Now the next is ox, post Taurus. So I just type like ox. Now I remove the first line of the FASTA format, paste the sequence alone. Now I can go with the what is this actually? Canis lupus. Okay, Canis lupus. I can type like Canis. Okay, I remove the first line, and so like this we have to prepare. There are some thing we have to prepare initially, or it won't work. Caviar. I think one is Guinea pig and the other is dog. The Canis is dog, isn't it? The other is a Guinea pig. Okay, so we have given this according to the format. Now whatever I prepared, I'm going to save as .txt. So I give like insulin.txt. Okay, insulin.txt. Or simply just type like this. It will be saved like insulin.txt. So we can check whether it's saved like insulin.txt in properties. Show more properties. Yes, it's insulin.txt. Now see how we are going to work with the protest. Type protest. We got like this. What is that? Capital insulin dot txt, capital I. Yes, capital I. So I'm going to type insulin, whatever newly created file, insulin dot txt. We got this information. I just reduce the font. Okay, so we get like all these settings correct. If the settings are correct, type Y. So I'm typing Y now. Press enter. Sequences out of alignment. Enter to quit. There is some problem. So whatever file we have created, there is a problem. So we have many characters in the sequence. So I'm going to take only few characters. I remove. I take only around 20 characters. So I just selected the 20 characters and I'm deleting it because if you have a more characters, it won't work. So that's the thing out of box. So I'm removing. I just have few characters, and now I have something like 40. Okay, file save. So I'm going to give this input once again. Protest. Give the same kind of an input incident.txt. Whether you want to create a new file or create a new file, uh, replace replace it or append it. Replace. I want a replace or a new file if you want to create capital F. Please enter a new file. I'm going to give like out file. The out file that you want to is already exist. You want to replace? Yes, I want to replace. I click R for replace. Now are the settings right? We are using T for lead, Jones Taylor Thornton Matrix, JTT. If you want Kimura, we have to type the keyboard P. Enter pre and press enter. Now it has changed to Henikov. It came to the Henikov, but we want Kimura. So again we have to type capital P, enter. Now it has changed to Tehoff. So after Tehoff map, then only you get Kimura. So again you have to type capital P, enter. Now it has changed to Kimura. So whatever we have said, okay, we have to, if the settings are right, click S. S. Sequences out of alignment. Please enter to page. Sequences out of alignment. So to work with the sequences out of alignment, we have to reduce the number of sequences. Or we can do one thing. If you want to practice with a kind of a sample file, we can use this as a sample file. I can better use this as a sample file, but we can also able to work with it. Can we reduce the size? This is the last attempt I can make it 30. And anything is even this character should not be more than 8. We don't have more than 8. So I think it's okay. Let us try with the chance. Protest insulin insulin.txt and now replace and now settings right, sequences out of alignment. So then I paste whatever I have. I pasted 5 and 13. So it is taking a still lesser. That's what we can understand. Okay, and again we have to. So even we should have a tab space or it won't work. Okay, now I save it as sample.txt. Sample. So now I work with the protest sample.txt. Want to replace and now capital Y. See, this is there is a problem with the software. I can check the I rectify this problem, okay, and then we can discuss the same on tomorrow. Okay, actually it works even with the sample file. Even whatever we have created is right, but there is a. I think I have to locate the folder somewhere in some drives and I can check it out. So tomorrow we can say about this. So any doubts you have other than this? So I just completed like even we can able to work with the Phylip tool, but tomorrow we'll be seeing more demo on few more tools. Yeah, I have to troubleshoot this software and I can make you work on tomorrow. Other than that, any doubts? If no doubts, thank you very much for your patience and even I thank you for participating in this session even on already. Have a great day tomorrow. Bye. Thank you.